So welcome back to part 3 of the video on Kummer extensions. So in part 1 and part 2 we have seen these two equivalent definitions of a Kummer extension. Namely, in both you start with a base field that contains a primitive nth root of unity. In the first you then take the splitting field over that base field of a polynomial of the form x to the n minus a, where that was an irreducible polynomial over the base field. That's a Kummer extension. And the second equivalent definition is you take a cyclic extension of degree n of your base field, and that will also be a Kummer extension. And we've proven how one implies the other in part 1 and part 2. So what I now want to do is show how, if you take a base field f that contains a primitive nth root of unity, and you create an extension by taking the splitting field over f of a polynomial of the form x to the n minus a, where now this polynomial x to the n minus a, it's still a polynomial in the base field, but I'm not going to insist that it's irreducible anymore. So if you take any polynomial of this form, create its splitting field, then this extension, I claim, is still going to be a Kummer extension. However, it's clearly not going to satisfy the definition of Kummer extension that we had originally, because the polynomial isn't irreducible. Or, well, if it is irreducible, then it immediately satisfies that definition. But if it isn't irreducible, then it's not obvious that it immediately satisfies definition 1. However, I'm going to show you that it still satisfies definition 2, and therefore it would satisfy definition 1, but not with this polynomial necessarily. So if this polynomial is not irreducible, then it's not with this polynomial that it satisfies definition 1. But by proving it satisfies definition 2, I've already shown that it will satisfy definition 1. It's just the polynomial. We don't know what it is, but there will be some different polynomial for which it satisfies definition 1 of Kummer extension. So how do we do this? So in this field k, which is the splitting field of this polynomial x to the n minus a, then there will be a root of the polynomial. So let's call that root alpha. So alpha is an element of k and alpha is a root of the polynomial. So that means that alpha to the n is equal to a. Then again, it is the case that k is equal to f adjoin alpha, and this is for the same reason as we saw earlier, because once you've got alpha, then you've got all the other roots to that polynomial as well, because you've got the other roots will be alpha times zeta n to the I, where I can be 0, 1, 2, all the way up to n. So the moment you join on alpha, you're immediately going to have alpha times all these powers of zeta n, because zeta n is in the base field, and therefore you're going to have all the roots to the polynomial, and therefore this is equal to the splitting field. Good, so it's a simple extension. It's the splitting field of a separable polynomial, so all of these are distinct for the same reason as we talked about earlier. So we know all of the powers of zeta n from 0 to, this should say n minus 1, because otherwise n would be the same as 0. All these powers are going to give different elements of the field. None of them are equal to one another, and therefore alpha times them is also going to be a different element of the field. I suppose I should just add that alpha obviously doesn't equal 0, because 0 isn't going to be a root of this polynomial, because if alpha was 0, then of course all of these would be the same element, but because alpha is non-zero, they're not going to be the same element, because if two elements were the same thing, so if you had alpha times zeta n to the I was equal to alpha times zeta n to the j, where I doesn't equal j, well, you can multiply through by alpha's inverse, because alpha doesn't equal 0, and then you'd get a contradiction, because you'd have some smaller power of zeta n. You'd be able to, the alpha would go, and you'd then have zeta n to the I is equal to zeta n to the j, and then you'd be able to cancel whichever one is lower, and then you'd have some smaller power of zeta n giving 1. So that will contradict zeta n being a primitive nth root of unity. So it is important to acknowledge that alpha doesn't equal 0, and that's how we're concluding that all of these roots are distinct. So therefore this polynomial is a separable polynomial because it has its degree number of distinct roots. Therefore this is the splitting field of a separable polynomial, ergo it is a Galois extension, a finite Galois extension. So now we can consider what its Galois group is, and I'm going to show you that its Galois group is cyclic. So again, because the field is F adjoin alpha, then the automorphisms in the Galois group of K over F are going to be completely determined by where they send alpha. Once you know where alpha goes, it determines everything. And they're going to have to map alpha onto another root of this polynomial, because any polynomial satisfied by alpha, whatever alpha is being mapped onto, it still has to satisfy that polynomial. Sorry, I should reword that. Any polynomial with coefficients in the base field that alpha satisfies, then whatever alpha is mapped onto by a F automorphism of K, it's still going to have to satisfy that polynomial in F, because the polynomial will be unchanged by the F automorphism. So it's therefore going to have to map alpha onto other roots of this. It's just now not the case that we can say that all of them will necessarily be automorphisms. So previously, when this polynomial was irreducible, we could conclude that the map that sends alpha to alpha zeta n to the I, where I varies over these, for all of them, we could conclude that it was a valid automorphism. Now we can't do that because we don't know that all of these roots have the same minimal polynomial, because this is not irreducible, so this is no longer their minimal polynomial. This polynomial is potentially going to split, we're handling the irreducible case. So I haven't said that, but, the non-irreducible case, the irreducible case, we already know that it's a Kummer extension. So we're handling the non-irreducible case here. So if this were reducible, then it would split into a bunch of lower degree polynomials, and then so if we split it into its irreducible factors, then the n roots that we've got here, they would be distributed amongst those polynomials. Some would be roots of one of them. So if it's split into f1 times f2 all the way up to fk, these are its irreducible factors, then some of them will be roots of f1, some of them will be roots of f2, some of them will be roots of fk, etc. So not all of them are going to have the same minimal polynomial, therefore, and they're therefore there's not going to be the isomorphism that there was before. We can't conclude that f adjoin alpha is necessarily isomorphic to f adjoin alpha zeta n the way we could before, when we knew they all had the same minimal polynomial. So we can't say that all of these are necessarily automorphisms anymore. However, we do know that automorphisms do exist, because we know this is a Galois extension. So and we know that they have to send alpha to one of these, and that once you know where alpha goes, it completely determines it. So some of them are still going to be automorphisms. So for some I in 0, 1, all the way up to n-1. Now 0 is a guaranteed one, because that's just the identity automorphism, so that's guaranteed. But for some of the other i's, they are still going to be F automorphisms of the field K. It's just now the case that not for all of them necessarily is it going to be true anymore. So what I can do is I can look at the smallest I value for which it actually still is an F automorphism, call that I0 here, and then I could call sigma my map that maps alpha onto alpha zeta n to the power of I0. So, of course, I'm not counting 0. 0 we know is an automorphism. I mean the smallest natural number one, the smallest positive one that actually remains a F automorphism of K. So this now, my claim is now that the Galois group of K over F is going to be generated by sigma. So it's going to be a cyclic group generated by sigma. So all the other ones are just going to be powers of sigma. Why is that the case? Well, it's a Euclidean division type argument. So if I had one, let's call it sigma twiddle, that wasn't a power of sigma, so it would be mapping alpha onto some power, so we'll call it alpha zeta n I twiddle. So it maps alpha onto alpha zeta n I twiddle. So I twiddle is the power that it maps alpha onto, effectively. And this would be somewhere in this list up here, I twiddle. It would be somewhere from 0 to n-1. But now what I can do is I can go up to the smallest multiple of I0 that's below it. So, if I have like I0, 2I0, 3I0, etc., I can go to whatever multiple of I0 is just below I twiddle. So maybe I twiddle is somewhere in between 2I0 and 3I0, and therefore I'd go to 2I0. If I twiddle was instead here, I'd go to below 4I0, then I'd go to 3I0. So I can go to the smallest the smallest multiple of I0 that is just below I twiddle. And then what I can do is I can take sigma twiddle and then compose it with sigma. Let's call that smallest multiple of I0 mi0. So in this case it would have been 2, m would have been 2, but more generally let's just call it mi0. So I can then go and compose it with minus m, not mi0, just m. So let me just rub this out. So minus m there. And now let's think about what this would map alpha onto. So sigma twiddle would map it onto alpha zeta n to the I twiddle, and then putting it through sigma to the negative m would then map it onto alpha zeta n to the I twiddle, and then putting it through sigma to the negative m, that would then multiply it by zeta n to the negative m I0. So what I then get, I twiddle minus, well, I'd here get zeta n to the power of, and let me just make some more space, I'll rub this out. So this would become zeta n to the I twiddle minus mi0, and whatever this is equal to here, it's going to be some number less than I0, because that was how I picked mi0, remember. So I went to the lowest multiple of, I did Euclidean division effectively. This is the remainder in Euclidean division of I twiddle by I0, and it's going to be therefore something that is smaller than I0, the gap between these successive values here. But that's a contradiction now, because sigma twiddle is an automorphism. This is an automorphism because it's an inverse of sigma, which is an automorphism to some integer power. Therefore, their composition would be an automorphism, and it would be mapping alpha onto alpha zeta n to some, I'll call it R for remainder, the remainder of Euclidean division, which is less than I0, which would contradict sigma being the smallest power value here, for which it was an automorphism. So that's how you can prove that the Galois group would be generated by this sigma that maps alpha onto alpha zeta n to the I0, where I0 is the smallest positive value in this collection of possible values for which it is actually an F automorphism. Brilliant. So that then proves that this is a cyclic group generated by this sigma. What is the cardinality of this cyclic group? Well, it's going to have to be some cardinality that divides n, because, you know, some power of this, let me pause to think for a moment. Yeah, I figured it out. So the I0 value here, it's going to have to divide n. Why? Because if it didn't, think about what would happen if it didn't divide n. Then when I take multiples of it, you know, when I do powers of sigma to the power of m is going to map alpha onto alpha zeta n to the mi0. If I0 did not divide n, then at some point I would pass n, you know, for high enough m's here, mi0 would eventually get past n. So for the small m's, it would be smaller than n, but then eventually it would pass n. And what I'm saying is it at some point has to actually land on n, because we're doing natural numbers here. M is a natural number. At some point this has got to equal n, because I'm saying I0 has to divide n. But if it didn't do that, then at some point it would land just beyond n. So, you know, if I draw a picture of this, sorry, I'm finding this quite difficult to explain, but this isn't actually complicated. So if you've got 0 here, you've got I0 here, and then you had 2I0 here, then you'd have 3I0 here, this is n here. So what has to actually happen is it has to perfectly divide it, and at some point it has to actually hit it. So in this case, in the case of this picture, this would be 4, 5, 6, 7, this would be 8. So 8 I0 would equal n in the case of this picture. But if that didn't happen, if instead, say, the last one fell here and then the one that's immediately above fell here, the problem is that that would then correspond to a power. You know, what would that be mapping alpha onto? That power, it would be mapping alpha onto alpha zeta n, and then it would be equivalent to this remainder bit here, which would be smaller than I0. So it's exactly the same sort of Euclidean division argument. It would contradict this being the smallest one. If I0 did not divide n, then there would be a smaller power that you could put here where it would still be an automorphism, because you could take these powers and get that smaller power. You could take these powers of sigma and it would remain obviously an automorphism, because powers of automorphisms remain automorphisms. And then you'd end up with an automorphism with a smaller power than I0 here, and that would contradict the definition of sigma. So that's why I0 does have to divide n. Right, so that means that what is the order then of sigma? Well, it's going to be this multiple of I0 that equals n. So m times I0 equals n, whatever that power is. And I might change my notation because I've used m too many times. I'll call this d now. So let's say d times I0 is equal to n. Then that means the order of sigma is going to be equal to d, and therefore this is going to be isomorphic to CD, where d divides n as well, because, you know, we've got that d times I0 is equal to n, therefore d divides n. Brilliant. So where were we? So what I have now shown you is that if you take the splitting field of a polynomial like this, where it's not irreducible, but it is over this ground field that contains a primitive nth root of unity, then I can immediately conclude that this extension that you produce is a cyclic extension of degree d, where d divides n. Now, if your base field contains a primitive nth root of unity, then it is going to contain a primitive dth root of unity, because if you consider zeta n to the power of n divided by d, this element, so n divides d, so this will be some integer here. Sorry, d divides n rather. Sorry, I'm speaking really badly. So d divides n, therefore n divided by d is some natural number. So I've got some power of zeta n here, but this element, if I raise it to the power of d, it will give me 1, because I'll get the zeta n to the power of n, which is 1, and no smaller power is going to give you, is going to make it go to 1, because those smaller powers, if it did, those smaller powers would also be a smaller power of zeta n than n that would be giving 1. So this is a primitive dth root of unity in F. So I've now got a cyclic extension of degree d of a base field that contains a primitive dth root of unity, and therefore by my second definition of Kummer extension, this is a Kummer extension. So there will be some other polynomial, something of the form x to the d minus, let's call it a bar, which is irreducible over the base field f, where this extension satisfies the original, the first definition of Kummer extension with that polynomial. We're not going to try and work that polynomial out. We don't need to. All I want you to take from this is that if you generate the splitting field of any polynomial of this form over a base field that contains a primitive nth root of unity where n is the same as the power here, you get a Kummer extension. Not necessarily a Kummer extension of degree n, but you get a Kummer extension of some degree that divides n. If it's irreducible, then you get a Kummer extension of degree n. If it's not irreducible, if it's reducible, then you're going to get a Kummer extension of degree d that divides n. So what this actually shows us, no, actually, I won't make that comment. I don't think that what I was about to say is quite true. Excellent. So I think we'll probably leave it there. I don't think I have much more to add. We will use what we've just done in the final video here quite a bit going forward. This is an important concept, that splitting fields of this form on top of base fields that contain the right primitive roots of unity are going to be Kummer extensions. And therefore, you know, we know Kummer extensions are all simple radical extensions. We know that they are cyclic extensions. And therefore they're abelian extensions. An abelian extension, just in case you don't know, an abelian extension is a Galois extension where the Galois group is abelian. So because they're cyclic groups are always abelian, so they are therefore abelian extensions. So I think we'll leave it there, and we'll continue in the next video with cyclotomic extensions.